Thanks for the introduction. And yeah, thanks to the organizers for giving me this great spot, first talk of the conference. So everyone's very much awake. And I want to tell you something about computation of persistent homology. So it falls in the area of topological data analysis, and this is some recent progress on software for computing the persistence barcodes for the Vietoris-Rips filtration. So let me just give you two slides without words on persistent homology as a reminder. So this is, if you've been here last week, you should have seen this. The idea is, and probably many of you have seen it in some way before, so the idea is you want to have a point cloud, so topologically this is discrete, but by somehow connecting the points based on their proximity, we create a filtration of topological spaces, and we want to study the homology of these spaces with coefficients in a field, so we can construct something like the persistence barcode. And as you can see here, when we connect the points, here the construction we see is not the Rips complex, but the Delaunay complex, because this is something you can draw on the plane. And we have short-lived cycles that will be filled very quickly, and then we have long-lived cycles. Here is you can recognize a cycle circling around the hole in the middle. This is kind of the most persistent feature, and that's what you recognize as the circular shape, as the donut, if you want, in this picture. So this is the object that we want to study. This is the filtration. Here are the 4 steps of the filtration that I've shown. And on the bottom, we have the persistence barcode. The persistence barcode really describes in one simple picture the entire homology of the filtration at each scale individually, and also how different scales are connected. If I pick one value from the parameter range corresponding to the distance value 0.1, so everything that's closer than 0.1 is connected, and then 5 intervals in the persistence barcode. The persistence barcode is simply a collection of intervals. The vertical orientation is not meaningful here. This is just for visualization. And the horizontal direction is the scale parameter direction.
This is H1.
This is H1, exactly, very good. So what we see here, so this is only for H1. I look at the parameter value 0.1, 5 intervals contain this value, and this tells me that H1 is 5-dimensional. I'm working with field coefficients. And moreover, when I compute persistent homology, I actually compute for each of these intervals one cycle that generates the homology across its lifespan, and at the death point it becomes a boundary. And moreover, when I look at 2 scales at the same time, I simply have to look at the intervals that contain both values. That tells me the rank of the map induced in homology by the inclusion from one complex to another. So the inclusion of this complex into this one has a 1-dimensional map map with rank 1 in homology, and here is a cycle associated to this bar that's still a non-trivial cycle. Like it's a non-trivial at 0.4, still non-trivial at 0.2, still non-trivial at 0.4, and that's really this subspace of the homology at the larger scale is really the persistent homology connecting these 2 scales. And what we have seen last week algebraically, what the barcode describes is the isomorphism type of the entire diagram of homology groups connected by linear maps. So this is kind of a representation theoretic point of view, and this isomorphism type is completely encoded in the barcode. That's why we can read off this information: pointwise dimensions and pairwise ranks. So this is, and what we also have seen last week is this barcode, the structure, the geometry of the barcode, if you want, is stable, meaning if I perturb the input data just a little bit, then also the barcodes will move just at most this much. So I perturb by delta my input points, and the length, both endpoints of the bars will change by at most delta. You might have some new ones appearing, and they, as a result, they have to be short. And on the other hand, short ones might just disappear. So this is stability, and this tells us that the information we get from the barcode can be interpreted in a meaningful way, even in the presence of noise. Okay, so we want to compute this. This is computational topology, so we actually want to have software to compute this, also for very large data sets. One thing we often like to work with is this metric instead of geometric construction, if you want, of Vietoris-Rips complexes, where we take as an input not just Euclidean space, but we can have any finite metric space. And often in situations for data analysis, this is more convenient. You have some way of associating a distance, but it doesn't have to be a geometric one. And then, so we define the Vietoris-Rips complex. So X is our underlying point set, and a simplex S in the Rips complex is simply a subset of this finite metric space with diameter at most T. T is my scale parameter, and I want to vary this scale parameter, and I want to know what the persistence barcode is as I change this scale. So it's completely defined by the one skeleton, by all edges that have a certain pairwise distance below my threshold, and then I add in all higher simplices. So it's a flag complex. This is the construction behind the software, and the goal is to compute the persistence barcodes. So there's one barcode for each homology degree, and we want to compute up to dimension k. Okay. Let me give you a demo, because this is something you can try. Okay, I want to mention something else. I try to be slow in my talk, but it never quite works. And if you have seen something on a previous slide and you want to look back, here's the URL of the slides you're seeing here, so you can check on your mobile device if you missed something. Okay, so let me switch to the browser, where you can see a live demo of this software. So this is implemented using C++ to JavaScript compiler, or in Google Chrome they have a different method called portable native client, so you can run native code at native speed inside the browser. And since I'm lazy, I have an example that I can load here without doing anything else. You can see that it's loaded here from this URL. And this is the computation. So I'm computing persistence up to dimension 2. And yeah, it takes about 6 seconds, which tells you that this computer is actually rather slow. It works fast on my laptop. Okay, but so here you see the barcode in dimension 1, and here in dimension 2. You could also show in dimension 0, but for Rips, the interesting information actually starts in dimension 1. Okay, so let me switch back to my slides and put these results in perspective. So what the data set was is 192 points on the S2, and we wanted to compute the barcodes up to dimension 2, so we should somehow recover the two-dimensional fundamental class of the sphere. And that's yeah. Well, it's uniform distribution, yeah, and IID sample points. And so you see there's a kind of noise regime down here, so that's interesting for the random topology people, I guess. And then there's this feature that corresponds to the fundamental class, and there's no other feature in dimension 2. And this feature actually persists for a long range in the parameter range. So if you compare to the computation times first maybe it's interesting to mention the 3 skeleton that's used to define the homology here contains over 56 million simplices, so it's quite a big data set if you use this entire construction. And so here's a kind of family history of persistence computation software, going from Java, Plex Dionysus, Goody, Diva, Irene. So you see that and every iteration, if you want, some ideas from the previous developments have been carried over and improved. So we have a big improvement already going from JavaPlex to Irene. And Ripser is still, again, like by a factor of 10, faster and less memory than Irene in this case. So you see that there's a lot of progress being made on these computations, and we still haven't reached, it seems we still haven't reached quite the limit, which is also good because computation is still seen as one of the main challenges in topological data analysis because of the kind of blow up that you see here from just a few hundred points to million simplices. So this kind of progress is really very important and highly needed. Okay, let me summarize what the software is. It's only about 1,000 lines of C++ code, self-contained, no dependencies, and we're supporting computation for coefficients in a prime field. Sparse distance matrices, so if you don't want to go all the way through the range, this is quite important. You can actually, using this, you can compute much larger data sets if you stop at some distance threshold. It's open source, released last year, followed by this online version that I've demonstrated a month later. And right now for these typical computations, it's the most efficient software for Vietoris-Rips persistence. As an example that I did here with the code 50,000 points and on a torus embedded in R3, and I wanted to compute the H2 barcode. I think this is an example that Jacek suggested, and it took about 2 minutes, 9 gigabytes. So this is not, I think the main thing to point out is this is without doing any approximations. This is the true correct barcode. And I'm also very proud to say that a couple of days after this has been suggested, it received a Best New Software Award at ATMCS together with Rivet, that's a visualization tool for multidimensional persistence by Michael Lesnick and Matthew Wright. Okay, so this is a summary about the software Ripser. Let me say something about the design goals that started this project. I've been involved in a couple of other projects for computing persistence, and the goals were slightly different. For the first project was FAT, and for that we tried to somehow optimize the main computational part of persistence, which is the matrix reduction, and we wanted to understand why certain things work so well and how different optimizations play together. And the second project, Diva, this was mainly focusing on distributed computation, so we wanted to run these computations on a big cluster. And now for Ripser, the idea was really, like the first idea was just to try to focus on memory efficiency. Most of the time before, people had focused on time efficiency, and I just wanted to be able to compute larger instances. Maybe it could take a week, but I didn't care, but I wanted to just be reasonable about computation time. And surprisingly, what I found out was in the end, the code turned out to be faster than what I had before. And the reason is that memory access is typically slow, and if you can recompute something very quickly, then that may pay off in comparison to reading it from memory, which can be maybe 100 times slower in some cases. So, but I was a little bit surprised to see that. So the main focus should actually only be efficient about what you actually store. So I think there's 4 main points, 4 main observations or optimizations that are playing a central role in Ripser, and 2 of them have been discussed before and implemented before. The first one is clearing is inessential columns, so certain parts of the matrix algebra don't have to be performed if you want to compute homology. The second one was an observation made by Vinod Silva and Mikkel and Dmitry Morozov that computing persistent cohomology in certain cases can be much faster. And I will give you a simple counting argument, at least providing intuitive explanation for why that should be true. And then there's two new things. Implicit matrix reduction, which means that some of the things are not, some matrix computations are not really stored in memory. And then there's also an interesting Morse theoretic aspect that gave another bit of improvement in running time, connecting discrete Morse theory to persistent homology and making use of the connections that you find there. So let me start with the first. So one thing I want to mention, what we learned from FAT, where we compared all the optimizations that have been around before, we found that clearing and cohomology can give you large speedups in computing Rips complexes, but that seems to only work when you use both at the same time. And if you just use one of them, you can actually get even worse. So that's a kind of, interesting observation, and that will also become evident from the simple counting argument I will give later why that's the case. Okay, so I will tell you a little bit what the main algorithmic idea behind this persistence computation is in the form of a matrix reduction algorithm. So as I said, we are starting with a finite metric space of endpoints, and we want to compute the persistent homology of the Rips filtration. And so we're setting up the boundary matrix for the entire, so for the last complex in the filtration, the full simplex if you don't stop earlier. D is the boundary matrix of this filtration. My basis for this matrix is simply the canonical one, ordered in filtration order, somehow breaking ties when simplices appear at the same time. And my notation for the ith column is R index I. And the algorithm, there's a question? Oh yeah, so R, so this is another matrix. Ri is the ith column of some matrix R, and this other matrix R will, I start with a matrix D, and then I modify it, and this is kind of, so the meaning of this Ri will change over time. The algorithm is quite simple, only 3 lines. I start with a boundary matrix, and I start with another matrix storing the coefficients. I start as the identity matrix, so this just records the operations that are performed on the boundary matrix. And then, while I have 2 columns with the same pivot, the same row index, last row index with a non-zero entry, then I'll add the earlier column to the later column in the filtration. So I add from left to right. And that's the algorithm. So you might think that there's not much to computing persistence. Of course, the devil's in the detail. But the important bit to remember is not what the algorithm is, but what it should produce. We have a matrix R, which has unique pivots. So every 2 columns have different pivot indices. And it obtained from the boundary matrix by multiplication by a full rank upper triangular matrix. That's all I want to have. Okay? And that's what my code should produce. Okay, so to understand why this tells us homology, let's call those indices which lead to an empty column positive, because they actually correspond to the birth of homology in the filtration. And the ones that have non-zero columns are negative indices. And the positive ones which do not occur as pivots in any of the negative columns are called essential. The reason is that those are the ones that create homology that is not killed later in the filtration. So they correspond to essential homology, the homology of the final space that I'm filtering. And it's straightforward to verify that if I take the columns from my matrix V, the matrix V encoded the coefficients for the reduction, and the positive ones, well, if I apply the boundary matrix, I get something empty, so they're clearly cycles, and indeed they form a basis for the cycles. And on the other hand, well, the reduced columns that are non-zero form a basis of the boundary. If you think what this reduction does, it really turns the boundary matrix into a bunch of linear independent columns. But so for homology, this is not convenient because this basis is not the basis of boundaries is not a subset of the basis of cycles. So we're going to perform a basis exchange, and instead of using all of these basis cycles that we have here from the matrix V, we simply take all of the boundaries that we already found, and then we add the essential ones. And now we have we have a construction for a basis that's compatible, and we can simply take the new ones, we take the boundary basis and we extend it to a cycle basis, and those cycles which we added are exactly generators for the homology. So that's what we need for persistence computation, right? And if now the message of the slide is when you look at the computation this way, we actually have performed quite a bit of computations that are completely unnecessary for the problem. Namely, the columns that have a positive but non-essential index, the columns appearing in this set of pivots of the reduced matrix, they're never used, and there's actually a very large number of them. So it doesn't make sense to even touch the matrix on this column. So of course we have to know where these columns are before we start touching them, but that can save you a lot of time. So even though we have a very simple algorithm, just blindly applying the algorithm would lead to a big waste of effort. So that was the observation made by Chow and Michael. Don't reduce at those non-essential positive indices. And one way to do this, one way to find out where not to reduce, is to not perform the computation in all homology degrees at once, but you start in top dimension and you go down. And then whenever you find an index that's a pivot of another column, then you simply set this column in one dimension lower to 0, because you know that's what you just learned. This is one column you don't have to touch, and it will become 0. What's also important, I think that wasn't observed by Chow and Michael, that you can even recover the V matrix, the coefficient matrix, because now for this index you simply need a cycle. You need some chain that's mapped to 0 by the boundary matrix, but you can simply take the one that you have here, the column Ri. So you have a boundary which serves the purpose of the cycle. And the point is you can indeed get the same structure. You can get the same matrices completely when applying this optimization. And this will become important for the later optimization. And one thing to point out why this is so helpful is that the kind of computations that we avoided here are typically much more demanding than the ones that we're left with. The positive non-essential ones take a lot of time to reduce. You reduce them all the way to 0, while the negative ones they're often even already reduced, and often they just take a couple of steps. And with clearing, you only left to reduce essential positive columns, and if you compute the Rips complex, there's all the way through the parameter range, then there's only one essential class in dimension 0 even. So there's very little hard work left to be done when you apply this. But I said it's not enough to just consider this clearing, right? The second point is applying cohomology. So we have seen many columns are not needed for the computation, and we can skip those. And now for cohomology, turns out that the number of indices that you can skip this way is simply much larger than the number of columns that you can skip when you compute homology. In a nutshell, if you want to understand what's the reason for this, if you want to apply clearing to the homology case, you have to start in some dimension, and then you still require to compute an entire basis for the k+1 dimensional homology of your k skeleton. And that typically is very large. This Betti number is very large, right? Because you're cutting away all the k+1 simplices and you're left with a lot of, so you're left with, k+2 simplices, and you're left with a large number of holes. And you're asking for this basis, you have to compute this basis, but you haven't even asked for this kind of information. And so this outweighs all the other benefits, and so in the end, if you apply clearing simply to persistent homology, you don't really gain anything. So on the other hand, if you do cohomology, the situation is much different, and you save a lot. And as shown by Vin, Mikhail, and Dmitry, the resulting barcode is the same. There's a kind of duality that's behind this result. Let me just do some counting to illustrate why you would expect to see the improvement only when you combine cohomology and clearing. So if you apply standard matrix reduction, you have to, and I'm considering the entire filtration of the full simplex. So we have d+1 choose n d simplices, and so this is the dimension of the d chains, and it factors into these sums, which give us the d-1 boundaries and the d cycles. And just inserting some numbers, we've seen the previous 65 millions, which distribute into 1.1 million negative indices and still 45 million positive simplices. So this is what I said before, that the positives clearly outweigh everything else. And now if I apply clearing, I don't have to reduce all the positive ones, just the ones in dimension k+1, but that's still 53 million instead of 54 million, so I really didn't win much. If I compute cohomology without the clearing, well, now I have 18. Well, this is kind of the dual positive ones. So I have 18,000 positive indices for cohomology and still the 1.1 million negative ones. If I apply clearing, I can get rid of a lot of those, and there's only one essential class in dimension 0 left, and this 1.1 million negative. This is the number of persistence pairs actually arising. So, and the reason why this part, so these numbers are still much smaller, so you might expect just from these numbers that cohomology already should be faster, but what's also important to keep in mind, so reducing those 18,000 columns is very costly because the number of rows is much larger. So this is the co-boundary matrix, and the number of rows is therefore the number of d+2 simplices. So this is enormous, and so this part here would also take a lot of time, turning this standard cohomology computation even more expensive. So only combining both at the same time can actually give you this big speed up. Okay. What we observed when we did these comparisons, we saw that the matrices we computed typically had just very few off-diagonal entries anyway, and most columns of the boundary matrix were reduced to begin with. We wouldn't even have to touch them at all. And of course, that's something, if you make this observation, you want to make use of this fact, and maybe adapt the algorithm to these observations. In the example I've shown, for example, we had 1.1 million columns that we needed to touch, and only less than 1,000 of them had actually to be modified at all, and the rest was already fine to begin with. So that's something you wanna make use of in your algorithms, and that leads to the idea of reducing the matrix implicitly. So the standard approach is, in almost all of the implementations, you write down the entire boundary matrix as it is, with respect to some ordering for the simplices. And then, so you generate this matrix and store it in memory, and then you apply the matrix reduction. And typically you only store the reduced matrix because that's sufficient to identify the pairs. Often the matrix V that encodes the operations applied to the matrix are not stored in memory. In contrast, what's happening in Ripser is the boundary matrix is not represented in filtration order, but I consider the boundary map in just a canonical order on the simplices, disregarding the filtration entirely. But that's something I can simply, well, the information needed to recover this boundary map is very simple, because all I need to know is what's the number of points and what's the dimension, because I label each simplex by a unique natural number, which is the number corresponding to the lexicographic ordering. And then I can simply algorithmically tell you what's the list of k+1 faces of this k-simplex. And spits out a list of numbers indexing the simplices in this co-boundary. So this is not something that this boundary matrix, which typically takes up a lot of memory, this is not something that needs a lot of information to describe and also to quickly recompute. So I'm not storing the boundary matrix, I'm recomputing it every time I need it. But I need to switch my representation from filtration order to standard lexicographic order, if you want. And then in my implementation, I really only store the coefficient matrix V, because my matrix R can quickly be recomputed. It's just the matrix V multiplied by this boundary map. And the boundary map, as I said, it can be accessed very quickly, even though it's not in memory. And this is good because typically this, as I said before, these coefficients, there's very few of them. And also the boundary matrix is described in very, very little information. So I reduced a lot of the description complexity of the problem this way. You could even push it one step further, and that's also implemented in Ripser. You can even get rid of the coefficient matrix, V. And here's an algorithm that can be, it's not obvious that it works, but it does. And so if you compare to the algorithm we have seen before, the only change is here. So now, before I added the ith column of R to the jth column of R in the reduction, now I decide to throw away even many columns of R, and I only add the column of the boundary matrix. So this also works. It takes a bit to prove that this actually works, but in the end, what it does, it recovers all the computations that have been performed before to get this column Ri that I replaced here by a different column. So the point is, here's an algorithm that computes the persistence intervals using only a single column of the matrix, and I don't need the entire previous columns, I just need one number for each previous column, which is the pivot of the previous column. So the point, if you want, from a matrix algebra perspective that's interesting about this slide is you can compute the rank of a matrix in O of n, like O of one of the dimensions of the matrix, pick the smaller one, right? And so this may become very expensive. I don't say anything about the running time, I just say something about memory, but it turns out that this is even practical, and it turns out to be, even though I'm talking about memory, it even turns out to be faster than storing than the previous algorithm, which stores the coefficients. Again, because this is so simple, I don't need to access previous computations. This is faster, I guess, mostly because many of the problems that we encounter in topological data analysis lead to very simple matrix computations. So use this with carefully, but I'm just saying in many cases it will lead to even better performance. So let me get to the final point. the notion of apparent and emergent persistence pairs, which lead to another speed-up factor of 3 to 10 in the implementation. And this is connecting persistence pairs and pairs in discrete Morse theory. To motivate this, let's consider what kind of different classes of filtrations we study in different aspects of persistence and Morse theory. So in general, when we talk about the theory of persistence, we don't make any assumptions on the filtration. So many simplices can enter the filtration at the same time. Discrete Morse theory kind of makes the fundamental assumptions that things appear either as singleton simplices or they appear in pairs. So we somehow made things a bit simpler already to get the main theorems. And in computation of persistence, I need to refine even further because I have to make the assumptions that one simplex enters at a time. I need to order simplex by simplex. So what's interesting here is that the discrete Morse theory perspective sits in the middle between two viewpoints on persistence, the theoretical and the computational one, which is very interesting. And it really tells you already that there should be a very close tie between the two. So let me say just one or two things about discrete Morse theory. So the basic notion of discrete Morse theory is that of a discrete vector field. And that's nothing but a partition of the cells of a cell complex into either single sets or pairs. The pairs here have to be like sigma tau, and sigma is a codimension 1 phase of tau. And typically this is visualized by an arrow from the lower dimensional to the higher dimensional simplex. And we call the singleton sets critical cells. So there's a brown critical 1 cell here and a red critical 0 cell. And so we also have a notion of discrete Morse functions whenever we have a function which describes a filtration. So sublevel sets are always subcomplexes. And the level sets, so the sets of cells with the same function value, they actually form a discrete vector field. Then we call such a function a discrete Morse function. And the vector field defined by a discrete Morse function is called a discrete gradient. And the main use for discrete Morse theory is describing homotopy equivalences combinatorially. So if we have a discrete Morse function and we have a range of values that doesn't hit any critical value, so let's take the example for the range from 2 to 5, then you can see that the sublevel set for level 5 collapses to the sub-level set for 2. This is the main theorem. And as a result, you can express the homotopy type of some cell complex using a discrete Morse function or a gradient field. And you know that there is a smaller, sometimes much smaller cell complex that's only built from the critical cells here. So in computation for persistence, this is often used for as a pre-processing step. So you take your filtration. The point is this all is compatible with the filtration. So these collapses are natural, and so they preserve persistent homology. And often it's used as a pre-processing step. You take a filtration of some chain complex, you modify it to a filtration of a smaller chain complex, and preserve the persistent homology. I'm using it in a slightly different way. And the reason is that the assumption that this pre-processing step, that this actually leads to speed-ups, it requires that the pre-processing itself is cheaper than the persistence computation. And as it turns out, those two steps in an algebraic viewpoint, they can be considered as kind of equivalent anyway. So it's a kind of, from a certain perspective, you can say that this is just a different way of expressing the same operations that we later apply in persistence computation. So I want to use discrete Morse theory in a slightly different way. And I want to identify a certain set of pairs that are both Morse pairs and persistence pairs at the same time. The way to set this up is we start with a Morse filtration. So we have one or two simplices appearing at the same time. And then let's consider what the two different types of pairs are in those theories. So the Morse pair says that inserting both simplices at the same time does not change the homotopy type, whereas in a persistence pair requires a simplex-wise filtration, and inserting the simplex sigma creates a new homological feature, and tau destroys that feature again. And well, here we talk about homology, here we talk about homotopy type. So you see that there's several. Here we have a Morse filtration, here we have a simplex-wise filtration, and here we have no change, here we have a change that's later undone. So there's three prominent differences between the notions of pairs, but there's a kind of intersection between the two. And the best way to express this is as follows. So we take a simplex-wise filtration, and we call pair sigma tau apparent if we have this symmetric relation. So sigma is the youngest phase of tau, youngest meaning appearing latest in the filtration, maximal index in the filtration. And at the same time, tau is the oldest co-phase of sigma. And it turns out this is a very good notion that actually seems to capture exactly the overlap between persistence and discrete Morse theory. So you can prove that any apparent pair, this should be pair, any apparent pair is a persistence pair, and at the same time, the collection of apparent pairs also forms a discrete gradient. And so the way this I came up with this definition is trying to generalize a construction that was used by Matt Cale for the study of random Rips filtrations in the supercritical regime. And he also found out that, so that gave a special case of this, which is very close to what I'm using in Ripser as well. And he also found that for this analysis, this construction had the property that it produced very few critical cells, which is also what I'm using in Ripser. And so here's two propositions connecting Morse theory to persistence and back. When you have a Morse filtration, and then you look at the pairs, the Morse pairs arising from this filtration, those will all be persistence pairs, they will all be apparent pairs, and they will have zero persistence. Now for persistence, you have to talk about a simplex-wise filtration, and I simply refine the Morse filtration in a canonical way. First the lower dimensional simplex, then the higher dimensional one. So this is how you can go from Morse to persistence. And you can also go back when you have a persistence. So you have an arbitrary filtration and you have a simplex-wise refinement. This is kind of the two filtrations that you need to talk about persistence. Then you can find a Morse filtration using the apparent persistence pairs from this simplex-wise refinement that sits exactly in between the two. So it refines the original arbitrary filtration and is yet again refined by the simplex-wise one. So this is how you can make precise that there is a close tie in between persistence and Morse theory that's exactly captured by these pairs. And so in the computation, I'm using something slightly different that's more natural during the execution of the algorithm. So the simplex-wise order I'm using is lexicographically refined Rips filtration. I start by increasing diameter, and then whenever I have simplices with the same diameter, I simply refine lexicographic in lexicographic order. And I can show that whenever I have a simplex tau in the co-boundary of sigma, so this is the lexicographically minimal proper co-phase of sigma, and it has the same diameter as sigma. And so if I detect such a situation, and I know also that tau is not paired yet, so there is no other persistence pair rho tau already found, then I know that sigma and tau are a emergent persistence pair. And that means by the time I notice this situation, I can stop enumerating further cophases. So this might happen when I enumerate the cophases of sigma in my matrix computation. This might happen very early, it might happen late, but whenever I'm here, I can stop and continue with the next. And that's how this lemma leads to another speed up. So it's a different use of discrete Morse theory. for computations, but it turns out to be very effective. It includes all the apparent pairs with persistence 0, and those can be identified very quickly. Okay, here's just as a final slide, a map showing, like Google Analytics shows me where people have accessed Ripser live, so there seems to be a large number of accesses from St. Petersburg. This is Munich, so I'm testing the code quite a lot, but you can see there's users all around the world. Okay, thank you.
Any questions?
Yeah.
Have you considered using a GPU to speed up some of these matrix?
Yes, considered. Yeah, I think some of these optimizations are clearly very much compatible with GPU, especially detecting when you have an apparent pair. You don't need to check anything globally. You just have to check the faces and the co-faces. Yeah, so that's something I wanna look into the future. I haven't done any implementation yet, but some parts of the computation are clearly well compatible for this. I mean, others aren't, but yeah. Huh?
Well, I really enjoy seeing JavaFX as the canonical example of a really bad improver. Have you considered contributing this to JavaFX?
I think the difficult part would be that JavaFX is written in Java and this is written in C++. So I don't know if it connects well with the.
Well, let me rephrase. How hard do you think it would be to port? Would we lose all the benefits?
I mean, I guess it would be kind of separate module for computing persistence, but it's a kind of self-contained thing, right? Because it will probably not make use of data structures that you have used or for the computation before, because the way the computation is done is so different, avoiding the entire boundary matrix. But yeah, I guess it could be done. I would try to avoid the effort for myself of porting this to another language, because I don't know if there's much benefit for this, but I think it should be possible in principle. But maybe maybe somehow things like what I did for the browser is more efficient, compiling it to something that you can use from Java.
Yeah, I couldn't get where actually did you use Vietoris-Rips complex and non-check complex?
Nowhere on the slides. I mean, this is just the implementation is about Vietoris-Rips. I don't use much of this.
All these same operations can be
Yeah. So this, I mean, the ideas I described here are much more general. It's just I'm using Vietoris-Rips. I mean, in the piece of code that enumerates the co-boundary.
as an input.
Yeah, but you could. I mean, many ideas.
Any filter.
Yeah.
But also I have another question, because it's the software is so fast. Did you find some interesting examples, natural examples, not artificial created, where different characteristic of a field later on? Because if you look for a circle or a torus, it doesn't matter which characteristic.
I think there are some. Yeah, you have to ask the.
Homology is the same, but some natural, not artificial. I could take, I could take projective space.
Yeah. I mean, so that's one example where.
Somewhere example coming from the real world where actually you can see the difference. Three different.
Yeah, no, but I think projective spaces are actually very very useful from an application point of view, and I think so. I haven't done much work on applications themselves, but yeah, I think Jose is not here yet, but he's been working on studying projective spaces, and he also used Ripser for this in one of his experiments. So yeah, and then it shows up the question whether you can see the difference. Very little actually, because it doesn't. I mean, the main point is that many computations could just consist of there's nothing to be done here, and that's true in any field. So these apparent pairs, they're persistence pairs no matter what coefficient you choose. They're actually persistence pairs with respect to integer coefficients. And then there's a little overhead, but it doesn't. It's not much. I mean, maybe 20% or something.
What's the running time in terms of
The running time in terms.
Yeah, so you look at-
So there was, I mean, this one. I have 3 examples here. So the one was 56 million simplices. Of course, not all of them are really involved in the computation here, but typically in other codes they are.
Oh, no, but do you have any guarantees?
No, I mean, there's no asymptotic analysis of the algorithm. I mean, we have this analysis of the matrix reduction algorithm that it's cubic, but this doesn't.
But you try to feed it experimentally?
No, not yet. No.
So what is the jump like if you have this example of a torus? Okay, what if you take a 3-dimensional sphere and you calculate H3? Would be like a significant bump?
I did that, so I computed H3 for 3 sphere with 1,000 points that took 20 seconds and less than a gigabyte. So I mean, I think the point is you can really, and I guess if you want to study something like the 3 sphere, you don't really want to go to larger samples if you don't have to. But yeah, but you can go pretty far now. I mean, as long as you use the threshold, it works quite well also for higher dimensions.
Okay, is there no further questions? Let's thank the speaker again.